In this capsule, we'll look at the relative stabilities of cycloalkanes. And there is a logical progression, at least in my mind, about why we are dealing with the stability of cycloalkanes at this point in the series. In the previous video, we talked about the stabilities of carbocations, and we have seen that carbocations tend to rearrange, and we looked at a couple of shifts called 1,2 hydride shift and 1,2 methide shift. Generally, secondary alkanes rearrange if possible to become tertiary. Let me rephrase that. Generally, secondary carbocations tend to rearrange if by doing so they become more stable carbocations. So, in that example we looked at, you had a carbocation like that and a hydrogen on the neighboring carbon that did the 1,2 hydride shift, which gave us, the more stable tertiary carbocation. Secondary carbocation became the tertiary carbocation, which made sense. Tertiary carbocations are more stable, so we didn't have any issues with that. Now, but we have seen another example where we had a carbocation like this, which is already a tertiary carbocation, but that rearranged to something like this, a secondary carbocation. So, which is not what is expected, because tertiary carbocations are more stable. Secondary carbocations become tertiary carbocations, but generally not in the reverse order. So what prompted or what makes this rearrangement move forward? What's the driving force? The driving force, we said, was the ring expansion, and the ring expanded because the cyclobutane ring here is less stable than the cyclopentane ring. Okay. The relief in angle strain, we talked about that. The bond angle here is 90 degrees in cyclobutane, the CC bond angle, CCC bond angle there. Whereas, since that's an sp3 carbon, the ideal bond angle is 109 degrees. The ideal bond angle is severely constrained, to 90 degrees here, which creates that instability. And by expanding to a 5-carbon ring, it relieved that angle strain. So now we are talking about those things led us to bring the stabilities or relative stabilities of cycloalkanes up for discussion at this point. Okay. So there's a roundabout way to talk about the relative stabilities of cycloalkanes, and in order to do that, we rely on some experimental data of one particular reaction. So this reaction at the very bottom, a general reaction, an alkane, when it is burned completely in oxygen, the products are carbon dioxide, water, and heat. That heat is called the heat of combustion. Did I write that somewhere? Combustion. It's like this, COM. Just to correct my accent issues. Any combustion. The heat liberated when an alkane completely burns in oxygen. So that heat, of course, increases with the number of carbons. So I have some data here from one of the textbooks I have. So the data shows the measured, so EXP is experimental, the experimentally measured delta H combustion heat that is produced during the combustion process. The minus sign there, the negative sign that you see here, just shows that the heat is liberated. And I have data for 5 different straight chain alkanes. I have the structures there. And there is data, for C8, C9, other compounds too, but lack of space here. And also we don't need to all the data. So you you see something as you move from C3 to C7, C3 to C4, you see, what do you see? You are adding, every time you increase one carbon, you are adding a CH2 unit to the previous one. So you take propane, you add CH2, you get butane, and then pentane, another CH2, hexane, another CH2, heptane, another CH2. And as you increase the number of carbons, the amount of heat liberated also increases. But yeah, that's true. Then we do something else. So we are trying to find out how much heat is liberated per methylene group. So let's look at it closely. C3 propane liberated that much. C4 butane liberated so much, so many kilocalories per mole of heat. So the difference between these two numbers represents the energy or the heat content of a methylene unit. So you see that going from C3 to C4, then the difference per methylene group, that extra CH2, which is called a methylene, which is here, CH2 is called a methylene unit. Methylene unit, the extra methylene unit in butane contributed 156.8. The extra unit in pentane, contributed 157.8, 157.3, 157.4, so on. And then after doing lots of, 20, 30 compounds, you can average the heat due to single methylene unit to be 157.4. You can see it's almost reaching that point there. And we have more data, not shown here. So scientists have experimentally determined that on average a CH2 unit contributes 157.4 kilocalories per mole towards the total heat of combustion of any given compound. So armed with that data, now let's move towards the right side of the picture here, of this table here. And here I have cycloalkanes. Under cycloalkanes I have a couple of columns, delta H, heat of combustion calculated, and the experimentally determined values. So since we know the value, the heat combustion of per CH2 unit, we have established that to be 157.4, of course from experimental data, averaging experimental data, and then we can turn around and apply that and use this data to calculate how much heat will be liberated when, say, cyclopropane is burnt. That's cyclopropane. It has 3 CH2 units. That's a CH2, that's a CH2, that's a CH2. So cyclopropane has 3 CH2 units. So since we averaged CH2 to be 157.4 in straight chain alkanes, 3 CH2s in cyclopropane, so calculated delta H for cyclopropane will be so much. Cyclobutane is this. It has 4 CH2 units. So 4 times 157.4, 629.6 is the calculated delta H for cyclobutane. So on for cyclopentane, you take this number, multiply by 5, and so on. So this is the calculated numbers here. So I just want to highlight that the column with the calculated numbers, this is the calculated numbers column here. Now on the right of that, we have the experimentally determined delta H for the cycloalkanes. Okay. So experimentally determined number is a true number. That's the heat the compound actually liberated. This is only calculated here. This green column numbers are calculated. These are actual numbers, experimentally determined numbers. So you do see that there is they do not match up every time. Okay. So the experimentally determined heat of combustion for cyclopropane is much more than the calculated number. The difference being 27.6 kilocalories per mole. So cyclopropane actually contains much more energy then calculated, and that by that much, so many kilocalories per mole. So that means that cyclopropane, and okay, we'll come to that. So you see that as we move from cyclopropane, as we increase the ring size, the calculated numbers and the experimental numbers are coming closer, and at one point you see 6-hexane, hexane, the straight chain hexane, and cyclohexane. Cyclohexane and the straight chain hexane have the same amount of energy. See? Not the same amount of energy, because the amount of energy that's liberated is different, but since we calculated the 6 CH2s per CH2 is this much, the 6 CH2, so this is the calculated one, this is the experimental one. So for cyclohexane, the calculated and experimental numbers are pretty close, 0.1, and some textbooks even say 0. So we say among cycloalkanes, cyclohexane is the most stable, whereas cyclopropane, because it has all this extra energy, that's the least stable. So you can see from this order, cyclopropane is the least stable, followed closely by cyclobutane. Cyclopentane is somewhat more stable, cyclohexane is more stable, somewhat more stable, but cyclohexane is the most stable of all. And surprise, nature uses the cyclohexane ring quite a bit. For example, I need to erase all these things. You can see cholesterol, which all of us are familiar with the name at least, contains 3 cyclohexane rings and a cyclopentane ring. So cholesterol looks well this. It has 3 cyclohexane rings and 1 cyclopentane ring, and of course there are other bits, but we're just looking at how nature uses them. And then we have been working in our lab with some compounds that look like this. That is the other one now. So 5, 7, 5. And in penicillin, that doesn't mean you do not see the cyclopropane and cyclobutane rings in nature. They do occur, but less often. So you see, by this using the experimentally determined numbers for the straight chain alkanes, we were able to extrapolate that data into the stability of cycloalkanes. So there we stop. And there are reasons why cycloalkanes, like example, the lower ones, lower alkane numbers like C3, C4, compounds like this, it's easy to see that the bond angle here is like 60 degrees, whereas the sp3, these are sp3 carbons. Each carbon of cyclopropane is sp3 hybridized carbon. The ideal bond angle is like 109.28 degrees, so which is in cyclopropane severely constrained. So there's a lot of angle strain here. Angle strain. And since I do not have models here, I cannot show you that, but there's also something called torsional strain. So 2 types of strain contribute to this higher energy that is in cyclopropane. Now, cyclobutane is 90 degrees, so it's somewhat, the angle strain is somewhat relieved, but still there is some. So cyclobutane is also less stable than cyclopentane, somewhat less stable than cyclohexane. So that is a logical continuation of what we were talking about in the previous video. And this whole series so far we're talking about the stability. Stability is an underlying factor, an important factor in predicting the products of reactions, whether the reaction go this way or that way, what's intermediate, which one is more stable intermediate, so on, so forth. So we still have a couple more things to go on stability, about the stability of alkenes. We'll talk about that stability of alkenes in the next video.